Welcome to the deep dive. Today, we're strapping in, really, for a high-speed tour through, well, the foundations of reality.
Yeah, we're going deep into the laws of science.
Those, crisp, elegant mathematical truths, the ones that dictate how everything operates from the smallest bits to whole galaxies.
Exactly. And our source material is this great mix. It catalogs the laws, but also gives us these intimate, sometimes pretty shocking stories about the people who found them.
Right. So the mission today really is kind of twofold.
I think so. First, just appreciating the shocking elegance of it all, that nature allows these simple laws. And second, really understanding the human side, the genius, sure, but also the rivalry, sometimes the madness behind it all.
What immediately jumps out, looking at the sources, is just how mathematically neat those early laws are. It's often basic algebra, stuff you could almost scribble down quickly.
Precisely. It's like what the philosopher Rudolf Carnap pointed out. It's, surprising and frankly fortunate that nature often lets itself be described by pretty low-order math functions.
Low order meaning simple, like Boyle's law.
Yeah, exactly. Like P times V equals a constant. Simple multiplication, equality. It's concise, it's elegant, and it explains a lot.
And crucially, these early laws, the elegant ones, they usually share that key thing, eponymy. They get named after someone.
And that naming tradition immediately points us towards, well, the chief architect of the modern world, Isaac Newton.
Right. The man whose laws of motion and gravity basically defined our view of the universe for centuries.
But the sources, they show a life lived often right on the edge. He was born into this world of darkness, obscurity, and magic, as they put it. And we know he apparently veered at least once to the brink of madness. It really sets the stage, doesn't it? Discovering order often came from deep personal chaos.
Okay, let's unpack that. This contradiction between the beauty of the law and the complexity, the messiness of the lawgiver.
Because the scientists who got their names on these laws, they were incredibly diverse, often real polymaths, just stunning intellectual range.
Like Jean-Baptiste Biot, the French physicist.
Exactly. This guy wasn't just happy with one field. He's doing applied math, astronomy, elasticity, magnetism, optics, mineralogy.
Wow.
Yeah, a total human dynamo. They even named the mineral biotite after him. Which seems fitting, right? For someone working across so many areas.
But the sources also paint this, tragically human picture. When you look at their personal lives, it's striking how often wives died young. Gauss, Ampere, Kepler, Kirchhoff, Planck, Clausius. The list goes on.
It's a really painful pattern when you see it laid out. Take the French chemist Alexis Petit. His marriage was heartbreakingly short. His wife died just 6 months after they married.
Oh, no.
And the source suggests Petit himself then kind of suffered from this physical and mental lassitude, and he died before he even turned 30.
That's incredibly young.
It is. These minds were wrestling with the universe's biggest secrets while, dealing with the most acute, everyday human pain.
And if personal life was tough, the professional world wasn't exactly a peaceful haven either. The rivalries could be savage.
Oh, absolutely. You mentioned Newton. He was so sensitive to criticism, especially from Robert Hooke.
Right, the optics story.
Yeah, he literally held back publishing his masterpiece on light until Hooke was dead. That's how much it bothered him.
It wasn't just academic disagreement then.
No, it became deeply personal distress. After those early fights over his theory of colors, Newton apparently had a severe nervous breakdown. It just shows how tied up their identities were with their ideas.
And fame could be just as damaging as criticism, it seems. Michael Faraday introduced field concepts, lines of force.
His reputation soared, but his old mentor, Humphrey Davy, grew so incredibly jealous.
Jealous of his own protege.
Intensely, to the point where Davy actively campaigned against Faraday getting into the Royal Society.
Oh, that's petty.
It's brutal. And Faraday, too, suffered a nervous breakdown during all that. The pressure was immense.
And sometimes that pressure had the most tragic consequences. Ludwig Boltzmann, the Austrian physicist,
Father of statistical mechanics. His big idea was that heat wasn't some continuous fluid, but a statistical thing, arising from how countless tiny atoms move.
Okay, why was that so controversial? Sounds pretty standard now.
Well, back then, it flew in the face of the establishment view, championed by people like Ernst Mach and Wilhelm Ostwald. They just flat out rejected the idea that atoms even existed.
Really? They didn't believe in atoms?
Not in the way Boltzmann meant. And Boltzmann, who historians now think might have had bipolar disorder, His depression was just made so much worse by colleagues constantly forcefully arguing against his life's work.
That sounds incredibly isolating.
It was relentless intellectual persecution, essentially, and it took its toll. It seems to have directly contributed to his suicide in 1906. It's just a devastating example of the human price for pushing fundamental truth into a skeptical world.
That is, yeah, that's heavy. It really forces you to ask, doesn't it? If discovery is so tangled up with human flaws, rivalry, tragedy, is it even fair to stick one single name on a universal law?
Which brings us right to this idea of the eponymous trap.
Right.
Because the sources are clear, simultaneous discovery, that's the norm in science, not some rare exception.
The whole standing on the shoulders of giants idea.
Yeah.
If scientist A hadn't found it.
Scientist B probably would have, maybe a few months or a couple of years later.
And we see examples all over the place. for that.
Absolutely. The Mobius strip, Mobius and Johann Listing found it independently in 1858. Calculus Newton in England, Leibniz in Germany, basically at the same time.
Evolution theory, too.
Darwin and Alfred Wallace both reached the same core idea independently. Even something like the gas laws, Gay-Lussac and Dalton were both working on thermal expansion around 1802.
So it often just boils down to luck.
Yeah.
Who got to the printer first?
Pretty much. Or who had the better connections or wrote in the right language? Maybe the best example is Snell's law, for light refraction.
Named after Willebrord van Rooyen Snell, Dutch mathematician, 1621.
Right. But the sources trace the core idea back much further.
How much further?
Try the year 984. An Arabian mathematician, Ibn Sahl, correctly described the basic relationship, the foundation of the law.
Wow. Right.
Then, fast forward to 1602, Thomas Harriot, an English astronomer, rediscovered it independently, and this is key, he didn't publish.
So discovered in the 10th century, rediscovered by two people in the 17th century, but named after Snell, who published later than Harriot, who never published at all.
You got it. And just to make it messier, the French often call it Descartes' law.
Why Descartes?
Because he was the first to publish it using sine functions in 1637, though apparently his work didn't have the experimental proof, so it's like historical branding. It rewards the person who got it into the European scientific conversation most effectively, not necessarily the first discoverer.
That seems incredibly unfair, especially when you think about precursors who maybe didn't even frame it as a law, like Halley's Comet.
Perfect example, named after Edmund Halley because he did the calculations, predicted its return. Brilliant work.
But the comet itself
Had been seen for centuries, millennia even. Countless observers saw it long before Jesus' time. Eponymy often rewards the meticulous record keeper, the calculator, the promoter, not always the first person to see or understand the phenomenon.
Okay, let's pivot then, away from the chaos of naming in history and towards the power these laws give us. Because despite the messy path, these simple-looking equations have immense practical utility.
Absolutely stunning power, really.
Let's start with a classic, Archimedes' principle, buoyancy.
Right. The law sounds simple. The buoyant force on something is equal to the weight of the fluid it pushes aside.
And that simple idea explains, well, huge things, like why ships float.
Exactly. A tiny lead pellet sinks, right? It's dense, displaces hardly any water. But take that same amount of lead, shape it into a rowboat.
Ah, it displaces a huge volume, a huge weight of water relative to its own mass, so it floats.
Precisely. From battleships to you floating in the bath.
Now, Archimedes himself, there are some colorful stories there too, aren't there? The death ray.
Oh, the legend is fantastic. During the siege of Syracuse, the story goes, he built this giant array of mirrors to focus sunlight and set Roman ships on fire.
Did it happen?
Probably not quite like the legend says. Most scholars are skeptical. But it shows how his genius was immediately linked to these world-changing, practical, even weaponized ideas.
Okay, moving from water to the heavens. Kepler's first law.
Planets move in ellipses, not perfect circles, with the sun at one focus. Big shift.
And Kepler's motivation wasn't just looking at data, was it? It was deeper.
Oh, deeply theological. He saw his work as a quest for understanding the mind of God. He started out trying to fit the orbits into Platonic solids, these perfect geometric shapes. He was searching for divine harmony.
But even searching for divine harmony didn't stop earthly rivalry. His relationship with Galileo
Was pretty sad, actually. Galileo, his contemporary, was apparently quite dismissive. He refused to even give Kepler a telescope, knowing Kepler was poor.
seriously refused him a telescope.
Yeah. And later, Galileo just broke off contact entirely. Ignored Kepler's crucial idea about elliptical orbits, even though it would have helped Galileo's own arguments immensely.
Okay, let's talk fluids. Bernoulli's law.
Right, Daniel Bernoulli. The law basically says, speed up a fluid, its pressure drops, and vice versa. This is a real workhorse in engineering.
Examples.
The Venturi effect. That narrowing tube creates low pressure. It's why perfume gets sucked up into an atomizer, or how old carburetors mixed fuel and air.
And airplanes.
Critically important for flight. The shape of the wing makes air rush faster over the curved top surface. Faster air means lower pressure on top compared to the bottom. That pressure difference creates lift, pulling the wing up.
Simple principle, huge effect. But the family story behind Bernoulli's law, that's something else.
Oh, it's one of the most intense rivalries we found. Jaw-dropping, really. Daniel Bernoulli's own father, Johann.
Also a famous mathematician, right?
Yes. He was apparently monstrously jealous of his son's success, so much so that he published his own book on fluids, Hydraulica.
Okay, so competing work happens.
But the source suggests Johann intentionally put an earlier date on it, 1732, to make it look like his book came out before Daniel's key work, Hydrodynamica.
He faked the publication date to steal priority from his own son.
Seems like it. It wasn't just rivalry, it looks like academic sabotage. By his own dad.
Unbelievable.
Yeah.
The pettiness underlying such fundamental science. Okay, let's end this section on maybe a calmer note. Boyle's law. Boyle times V equals CO boy.
Robert Boyle, a very different character, known as the Christian virtuoso.
Meaning?
He deeply blended his scientific work with genuine piety. He truly believed that studying nature was a way to honor God, its creator. His motivation seems worlds away from the Bernoulli's cutthroat competition. It was devotion, not just ambition.
Okay, so we've seen the elegance, the utility, the human drama. But this history brings us to a really important point. What does this long story of simple named laws tell us about where science is now? There's this chart in the source, time, distribution of main entry laws, and the pattern is startling.
It really is. It gives us a massive clue about the shift. Look at the 19th century between 1800 and 1900. That's when, like, 60% of all these main entry laws were discovered.
Like 60%, the golden age.
The golden age of classical physics, absolutely, where these neat, low-order functions just seem to pour out.
But then, the 20th century. The
Right.
chart shows a crash. Only 8% of eponymous laws. What happened? Did we just run out of simple truth?
In a way, yes. After 1900, physics entered the era of, let's call it, non-intuitive science.
Meaning relativity and quantum mechanics.
Exactly. We moved away from laws you could grasp with simple algebra. Now we're into complex differential equations, tensor calculus, statistical probability, things that don't match our everyday experience at all.
Richard Feynman famously said about quantum mechanics.
Nobody understands quantum mechanics, even one of its creators. The laws we find now, they're not elegant in the same way byline times V is elegant. They're more like complex algorithms describing probabilities, not definite outcomes.
And this isn't just a conceptual shift, right? It makes doing science harder.
Massively harder. Steven Weinberg, the Nobel laureate, pointed this out. He said, physics might be moving into an era where the really fundamental questions, well, we might not be able to answer them with experiments we can actually build.
Why not?
The experiments needed to test the next layer of fundamental laws, think string theory or whatever comes next, they require energy levels, machines, budgets that are just astronomical, becoming practically, maybe even theoretically, impossible.
So where does that leave us? Is discovery grinding to a halt?
Well, that's the huge philosophical debate, isn't it? You've got Stephen Hawking, sort of the optimist, suggesting maybe we are close to finding the ultimate unifying laws, an end to the quest.
But there's another view.
Right. Isaac Asimov offered this powerful metaphor. He said scientific knowledge might have fractal properties.
Fractal, like those patterns that repeat infinitely as you zoom in.
Exactly. Asimov argued that no matter how much we learn, the knowledge that remains, even if it looks like a tiny slice, is potentially just as infinitely complex as the whole was to start with.
So the closer you look, the more questions pop up. The journey might just be endless.
A potentially infinite fractal coastline of knowledge.
That's quite a tension. The hope for a final answer versus maybe infinite complexity.
And it brings us right back to the source material's most provocative idea, something for you, the listener, to really chew on regarding the nature of reality itself.
You mean the idea that the laws, they aren't just descriptions, they're more like software.
Yeah. Paul Davies suggests this view. Maybe the laws of physics are like algorithms, the software running the universe, and all the matter and energy, that's the hardware, the giant computer.
And those simple early laws like Kepler's or Boyle's?
Could be like the foundational code, the operating system basics. And maybe when we look really deep down at the quantum level with all its weirdness and probability.
We're seeing the machine language
Mm,
beneath the algorithms.
perhaps. So here's the thought to leave you with. If these fundamental laws, these elegant rules we've talked about, were just algorithms running in some vast cosmic computer simulation, what does that actually mean for your perception of reality? Is it less real or just differently constructed? Are the laws simple because simple code is efficient?
That is definitely a mind-bending question. From
Yeah.
Newton's genius and near madness to the maybe infinite complexity of modern physics, and now the possibility it's all just dot code. What a trip through the laws and the lawgivers.
It really highlights the contrast, doesn't it? The beautiful math and the very flawed, very human discoverers.
Absolutely. Well, thank you for diving deep into this incredible catalog of human discovery with us today.